Welcome viewers to Gradient Daily. We are diving deep into the absolute bleeding edge of AI research, parsing through the technical details so you can stay ahead of the curve. I am beyond thrilled to be your host today because we have an absolute gem of an explainer lined up for you. We are taking a rigorous graduate-level dive into a research paper that has quite literally sent shockwaves through the computer graphics and AI communities. The paper is titled 3D Gaussian Splatting for Real-Time Radiance Field Rendering. It was authored by an incredibly talented team of researchers from INRIA and the Max Planck Institute for Informatics. Specifically, we're looking at the work of Bernhard Kerbel, Georgios Kapanis, Thomas Lehmkuhler, and George Stratakis. Whenever you see the backing of heavy-hitting academic institutions like these, it immediately tells us we are looking at paradigm-shifting work. If you have been following the massive explosion in AI-generated 3D environments, you already know that creating a photorealistic world from just a handful of standard 2D photographs has been the ultimate holy grail. But actually walking around inside those generated worlds in true real time with a high-fidelity visual style, that has remained painfully, frustratingly out of reach. Until now. So, grab your notebooks. Today's explainer is going to unpack the rigorous math, the specific algorithms, and the exact hardware benchmarks of how this team finally cracked the code.
Our breakdown today follows a strict six-part architecture. Number 1, impact of radiance fields. Number 2, the real-time bottleneck. Number 3, breakthrough 3D Gaussians. Number 4, optimization and density. Number 5, fast rendering algorithm. And number 6, discussion and future.
Section 1, impact of radiance fields, capturing 3D scenes. Okay, before we can truly appreciate the elegance of the solution presented in this paper, we really have to establish the spectacular technology that set the stage for it. Over the last few years, the ability to take a regular consumer smartphone, walk around a local park taking a simple video, and have an AI turn that footage into a complete explorable 3D scene has shifted from pure science fiction to actual reality. To understand the mechanics behind this, we must define a term you'll hear a lot: novel view synthesis. I want you to imagine you are watching a high-budget action movie in a theater. Suddenly, the director hits pause, the explosions freeze in midair, the actors turn into statues, and the camera freely detaches from its track, walking around the frozen, perfectly lit scene. It's much like that iconic bullet time sequence in The Matrix. Novel view synthesis is the computer science equivalent of that exact magic trick. Technically speaking, it is the process of generating completely new, totally unobserved viewpoints of a scene by extracting an underlying 3D manifold from a limited, highly unstructured set of 2D photos or video frames. You just feed the computer a scattered, messy collection of pictures of a bicycle, and the computer calculates the continuous geometry and the view-dependent lighting to perfectly hallucinate exactly what that bicycle looks like from any brand new angle while maintaining an incredibly photorealistic visual style.
The mechanism traditionally used to achieve this magic trick is continuous volumetric radiance fields. You probably know them by their famous acronym, NERFs. Now, how do these work? Imagine a room filled with a dense, infinitely detailed, microscopic fog of colored light. Wherever there is a solid physical object, like a chair, the fog becomes incredibly dense and opaque. Wherever there is empty air, the fog is perfectly transparent. A radiance field is essentially a continuous mathematical formula, usually powered by a massive multi-layer perceptron, or MLP, that represents that entire 3D space. Let's look at the math on screen, because this is crucial. This is calculated using the volumetric rendering integral. The expected color, capital C, of a single pixel along a virtual camera ray R is the integral of three things: transmittance, T of t, volume density, sigma of t, and color, C of t, evaluated from the near plane, Tn, to the far plane, Tf. So when rendering a scene, your computer shoots thousands of invisible rays out of a virtual camera. For tiny incremental steps along every single one of those rays, it has to ask the neural network to evaluate that integral, calculating the color and density of the fog at that exact 3D coordinate. This absolutely revolutionized scene optimization because it creates hyper-realistic, continuous scenes with an unprecedented visual style. But here's the catch. Asking a massive neural network to calculate that integral millions upon millions of times just to generate a single frame requires an astronomical amount of math.
Section 2. The real-time rendering bottleneck. The cost of quality.
That sheer computational weight of querying that continuous integral for complete, unbounded outdoor scenes, that is the massive bottleneck holding back the entire computer graphics industry. Researchers have historically faced a really painful compromise. Let's look at option A. Option A involves using large continuous neural networks like MIPNERF 360. The visual quality and the resulting style are jaw-dropping. It looks exactly like reality, but evaluating that MLP is incredibly expensive. Rendering just a single frame can take seconds, making real-time interaction or movement completely impossible. So then you look at option B. Option B involves discrete data structures or hybrid approaches like planoxels or instant NGP. These methods use voxel grids or hash grids to speed the math up significantly. However, they drastically struggle with empty space. They either require complex heuristic empty space skipping algorithms that severely limit their speed, or their memory requirements absolutely skyrocket because you have to store massive amounts of voxel data just to represent the empty, useless air in an unbounded scene. The trade-off was painfully clear. Prioritize the math for visual fidelity and style, or prioritize discrete structures for speed. The authors of this paper looked at that compromise and completely refused to accept it. They aimed squarely for state-of-the-art visual quality alongside true real-time speed.
So what is the benchmark here? The critical threshold for true, seamless interactivity is 30 frames per second at a full 1080p HD resolution. In the realm of vast, unbounded scenes, hitting this exact threshold means the difference between looking at a static, boring architectural mock-up and actually walking through a living, breathing virtual reality environment. Mathematically, why is hitting 30 frames per second so incredibly hard? It all comes down to memory bandwidth and flops, floating point operations per second. Traditional NeRFs trap you way below this 30 frames per second threshold because querying an MLP thousands of times per pixel for over 2 million pixels in a standard 1080p frame absolutely saturates the memory bandwidth of even the most powerful cutting-edge GPUs available today. The architecture simply cannot move the data fast enough from the memory to the processing cores to render the frame in 33 milliseconds. Achieving this speed without sacrificing that photorealistic visual quality requires completely rethinking how the geometry and lighting of a scene are stored and retrieved.
Section 3. Breakthrough. 3D Gaussian Splats. The core breakthrough. To solve this impossible bottleneck, the authors completely abandoned the massive, slow neural networks used in traditional NeRFs. They built an entirely new pipeline from the absolute ground up. They essentially broke the problem down into 3 methodical, brilliant steps. Step 1. Initialize the scene geometry using sparse points obtained entirely for free during the camera calibration phase. Step 2. Utilize an interleaved process of mathematically optimizing and controlling the density of explicitly defined 3D shapes. And Step 3. Implement a lightning-fast, visibility-aware rendering algorithm designed specifically for the GPU's hardware architecture. When you combine these 3 steps, this pipeline explicitly maps the solid geometry of the scene, eliminating the need to evaluate integrals in empty space entirely.
Let's break down Step 1, which starts with initializing from sparse points. When a construction crew builds a skyscraper, they don't just start pouring concrete into the air. They construct a skeletal scaffolding first. Sparse points are that exact scaffolding. When you capture a scene with photos, standard industry software, specifically a highly popular tool called ColMap, performs a process called structure for motion, or SFM. What SFM does is look at how specific pixels move between your different 2D photos to reverse engineer and calculate the exact 3D position of the camera for each and every shot. Now, as a totally free mathematical byproduct of this camera calibration process, ColMap spits out a sparse, low-resolution 3D point cloud. It is literally a rough, dotted skeleton of the physical objects in the scene. Previous NeRF methods largely ignored this free structural data, forcing their neural networks to blindly guess where the geometry began by querying empty space over and over. By initializing their 3D models exactly at the coordinates of these ColMap sparse points, the algorithm immediately anchors itself strictly to the actual solid surfaces in the scene. It entirely bypasses the calculation of the empty air in between the camera and the subject, instantly saving massive amounts of compute.
But, as you know, points are just infinitely small dots. They cannot represent continuous solid surfaces, and they certainly don't look photorealistic. The brilliant solution here is to attach explicitly defined 3D Gaussians to this sparse scaffolding. Let's look closely at the math on the slide. A 3D Gaussian is defined by this specific equation. G of x equals e raised to the power of -1/2 times x minus mu transpose times the inverse of sigma times x minus mu. It looks intimidating, but let's break it down. It is parameterized by a 3D covariance matrix, sigma, and a mean, mu, which is quite simply its x, y, and z coordinate in 3D space. I want you to think of these not as rigid blocky pixels, but as uniquely shaped semi-transparent water balloons of paint. Because they are mathematical bell curves, their opacity is extremely dense right at the mean coordinate in the center, and it smoothly fades out toward the edges based on that covariance matrix. When you stack millions of these together, their fuzzy edges blend seamlessly.
This perfectly preserves the continuous volumetric properties needed for gradient-based optimization. Now, to handle complex lighting and ensure a photorealistic visual style, the color of each Gaussian is represented by spherical harmonics, or SH. Spherical harmonics are complex mathematical functions defined on the surface of a sphere. This allows the model to accurately represent view-dependent reflections, meaning a puddle on the ground looks incredibly shiny and wet from one angle, but dull from another. Because these colored Gaussians exist at explicit physical coordinates, the computer does absolutely zero math in the empty space between them.
Section 4. Optimization and Density Control. Sculpting the Scene.
Placed on that initial scaffolding, these thousands of Gaussians initially just form a messy, unorganized blob. Sculpting them into a perfect 3D scene requires a mathematically brilliant concept called anisotropic covariance. Think of a perfectly round, spherical ball of dough. If you want to cover a completely flat tabletop, throwing a bunch of perfectly round spheres down will leave highly inefficient gaps everywhere. But if you take a rolling pin, you can squish that dough sphere into a flat pancake, or you can stretch it out into a long surfboard. Anisotropic covariance allows each individual 3D Gaussian to stretch, scale, and rotate completely independently along its x, y, and z axes. But there is a massive mathematical hurdle here. A raw covariance matrix, sigma, must remain physically valid. Specifically, it has to be positive semi-definite. If you just let an algorithm blindly optimize raw covariance values, it will easily create non-physical, mathematically invalid shapes that crash the render. To make this mathematically viable during training, the authors ingeniously decomposed the covariance matrix sigma into a scaling matrix S and a rotation matrix R. So, as you can see on the slide, sigma equals R times S transpose times R transpose. By optimizing the scale and rotation completely separately, the algorithm mathematically ensures every single Gaussian remains a valid 3D shape. This allows a single Gaussian to become a long, incredibly thin needle to perfectly represent a blade of grass, or a massive, flat disk to hug the side of a brick wall, drastically reducing the total number of mathematical primitives required to render the scene.
The architecture sculpts these shapes through an interleaved process of optimization and density control. It acts exactly like a rigorous mathematical gardener pruning a hedge. Every 100 steps during the training phase, the algorithm evaluates the positional gradient of all the Gaussians. Now, the gradient essentially measures how much moving a specific Gaussian would reduce the visual error compared to the ground truth reference photos. If the positional gradient of a Gaussian exceeds a very specific mathematical threshold, say 0.0002, it instantly triggers the density control mechanisms. This mechanism aggressively identifies two specific problems in the scene. First, it looks for under-reconstruction. This is where the physical geometry is missing, but the existing Gaussian trying to cover it is too small. Here the algorithm actually clones the Gaussian, creating a twin, and moves the copy directly along the positional gradient to fill the empty gap. Second, it looks for over-reconstruction. This happens when a single Gaussian is way too large and is awkwardly trying to cover an area with highly complex detail, like the intricate patterns on an antique rug. Here the algorithm forcefully splits the giant Gaussian into two smaller ones, dividing their scale by a precise factor of 1.6. By continuously interleaving this precise density control with the shape optimization we just talked about, the model organically evolves. It populates complex, dense geometry exactly where it is mathematically required and nowhere else.
Section 5. Fast Rendering Algorithm. Visibility-Aware Engine.
So we have this beautifully optimized cloud of millions of shaped Gaussians. How do we transform that into a real-time image on your monitor? The authors engineered a custom, aggressively GPU-accelerated visibility-aware rendering engine. When you move the virtual camera in the scene, the engine first mathematically projects the 3D Gaussians onto your 2D viewing plane. It then divides your entire screen into small, manageable 16 by 16 pixel tiles. It quickly checks which Gaussians intersect with which viewing frustrums. But here is the critical, foundational step. It utilizes a highly optimized, GPU-accelerated radix sort. A radix sort is incredibly fast on GPU hardware, and it uses this to perfectly order the intersecting Gaussians from front to back for every single tile on the screen. Once they are perfectly sorted by depth, the engine performs alpha blending, rapidly accumulating the color and the opacity of the Gaussians for each pixel. The absolute masterstroke of this entire rendering pipeline is this. The precise moment the accumulated opacity, known as alpha, reaches exactly 1, meaning the pixel is now 100% completely solid and opaque, the GPU thread entirely stops computing. It completely ignores all the thousands of Gaussians that might be hiding behind that solid wall. Imagine painting a window black. Once the glass is totally covered, you stop painting.
This dramatic reduction in memory bandwidth consumption and unnecessary flops is the exact mechanical key that unlocks the incredible 30 frames per second real-time performance.
Let's look at the rigorous empirical data to prove these claims. The researchers tested their novel pipeline against the absolute most demanding academic datasets in existence. They used the MIP-NERV 360 dataset, which is infamous for testing unbounded, highly complex outdoor backgrounds. They used tanks and temples, which is perfect for evaluating massive, large-scale geometric structures, and they used deep blending for complex indoor scenes. The results, running on a standard NVIDIA RTX A6000 GPU, are frankly staggering. For visual quality, measured in rigorous, standardized metrics like PSNR, SSIM, and LPIPS, they fully matched or outperformed the absolute best, painstakingly slow neural network methods. The visual style is flawless, but look at the rendering speeds on this table. On the impossibly dense MIP-NERV 360 dataset, they achieved over 135 frames per second at full resolution. On tanks and temples, they hit over 100 frames per second, and on deep blending, a blistering 190 frames per second. And remarkably, their training times remained highly competitive. They converged in under an hour for scenes that took previous state-of-the-art NERF models multiple days of continuous compute to train. They comprehensively solved the speed versus quality dilemma.
Section 6. Discussion and Future. Looking ahead.
Now, no graduate-level analysis on this channel is complete without objectively examining the limitations of the research. Bypassing empty space using explicit 3D Gaussians is a monumental paradigm shift, but it naturally introduces distinct challenges. Because the method relies on discrete, physically sculpted shapes rather than a continuous mathematical field, highly complex scenes with intensely reflective or transparent surfaces can occasionally trick the density algorithm. This can result in elongated, weird needles appearing in the background, or a frustrating phenomenon known as popping artifacts. This is where Gaussians visibly blink in or out of existence when the camera viewing angle changes too sharply, slightly breaking that perfect visual style. Furthermore, there is a very tangible storage cost. Storing millions of explicitly defined Gaussian parameters, meaning saving all their individual covariance matrices, their mean coordinates, and all their spherical harmonic coefficients, requires significantly more hard drive space. A single compiled scene might take several hundred megabytes of disk space, compared to the tens of megabytes required to store the pure mathematical weights of a traditional NERF network. Looking forward, the authors correctly point to the urgent need for robust memory compression techniques and more advanced optimization tuning to allow these incredibly detailed environments to be easily streamed over standard internet connections.
And that leads me to pose this critical, incredibly open-ended question directly to you. How will real-time 3D Gaussian splatting fundamentally alter the landscape of novel view synthesis and traditional rendering pipelines? Think about the massive ripple effects across industries. If we can capture reality instantly and render it perfectly at over 100 frames per second on consumer hardware without relying on massive server farms, what does this mean for the future of virtual reality tourism? What does it mean for indie game developers who can now physically scan a real-world forest, process it in an hour, and drop it directly into an engine, entirely bypassing the need to hand-model millions of polygons? The real-world impact of shattering the neural rendering bottleneck is going to be absolutely profound, fundamentally changing how computers understand, optimize, and display the physical world.
To solidify your understanding of this extensive lecture, here is your summary. If you remember only 3 fundamental concepts today, make it these. Number 1. 3D Gaussians explicitly represent a scene, completely replacing costly multi-layer perceptrons and mathematically bypassing empty space computation entirely. Number 2. Decomposing the anisotropic covariance matrix allows these Gaussian primitives to stretch and rotate validity, enabling incredibly accurate mapping of complex real-world geometry without non-physical artifacts. And number 3. A highly optimized GPU-accelerated Radix sort combined with an alpha blending engine smartly stops computing the exact moment opacity reaches 100%, ultimately unlocking massive real-time performance that absolutely shatters previous benchmarks.
What an absolutely brilliant piece of research. I really hope this deep dive gave you a true, rigorous understanding of the complex math and the innovative architecture working under the hood. That wraps up our explainer for today on Gradient Daily. If you found this PhD-level breakdown valuable and you appreciate the technical depth we bring, please smash the like button, hit subscribe, and ring that notification bell so the algorithm knows you want serious, structured analysis. We are parsing through the bleeding edge of AI research every single day, so be sure to check back tomorrow for another incredible paper deep dive. Keep learning, stay focused, and I will see you in the next one.